Welcome to AI Frontiers, where we explore the cutting edge of artificial intelligence research. Today we're diving into a revolutionary collection of 17 groundbreaking papers published on October 16, 2025, that are reshaping how we think about robotic intelligence. These aren't just incremental improvements. They represent fundamental breakthroughs where perfect reliability meets natural language understanding, creating robots that could transform everything from kitchen assistants to space exploration. Picture this scenario: a robot standing in your kitchen, listening as you casually mention you'd like a cup of coffee, then seamlessly walking over to the machine and preparing it perfectly. No programming required, no specific instructions needed. Just natural conversation, leading to flawless action. What seemed like pure science fiction just months ago moved dramatically closer to reality in 2025. This isn't a distant dream anymore. It's becoming an achievable technological milestone that demonstrates how far robotics has advanced. These 17 papers from Computer Science Robotics, known academically as CSRO, represent more than technical achievements. They showcase revolutionary advances that could fundamentally change how robots perceive, learn, and interact with our world. We're witnessing robots achieving perfect success rates in complex real-world tasks, humanoid machines understanding and executing natural language commands without missing a beat, and the emergence of truly intelligent robotic systems that adapt and learn like never before. The landscape of computer science robotics resembles a vast symphony orchestra where each instrument represents a different aspect of robotic intelligence: perception, planning, control, learning, and interaction. Just as a symphony requires perfect coordination between all instruments to create beautiful music, modern robotics demands seamless integration of computational intelligence, mechanical precision, and adaptive learning. This field tackles the intelligence layer, the algorithms and software that enable robots to make sense of their environment, reason about complex situations, and take appropriate actions. It's the difference between building a sophisticated puppet and creating a thinking, adapting entity that can handle unexpected challenges in homes, hospitals, factories, and space. The first dominant theme emerging from these papers is learning-based control and adaptation, essentially teaching robots the way you might teach a child, through demonstration, practice, and gradual improvement. The RMRL framework introduces role model reinforcement learning, where robots learn from approximately optimal examples rather than requiring perfect demonstrations. Meanwhile, the RL100 system achieves something remarkable: perfect performance across diverse manipulation tasks, completing 900 out of 900 episodes successfully. This represents a quantum leap toward the reliability needed for real-world deployment, where consistency and dependability are absolutely critical. The second theme focuses on vision-language-action integration, which gives robots the ability to serve as universal translators between human intentions and physical actions. The RoboGhost framework eliminates the traditional multi-step process of converting language to human motion, then adapting it for robots. Instead, it creates a direct pathway from natural language commands to robot locomotion, much like how you might instinctively reach for a glass of water without consciously planning each muscle movement. This seamless integration represents a fundamental breakthrough in human-robot communication. Space and aerial robotics emerges as our third theme, pushing the boundaries of where intelligent machines can operate. Think of it as robotics' final frontier, environments so extreme that human presence is impossible or dangerous. The Lagrange-Poincaré-Kepler equations work provides the mathematical foundation for spacecraft-manipulator systems operating in orbit, while other research demonstrates fully autonomous aerial construction using coordinated drone teams. These advances become crucial as we expand into space exploration and need robots that can work independently, millions of miles from Earth, where communication delays make real-time human control impossible. The key findings from these papers read like a collection of breakthrough moments that could reshape entire industries. First, the RL100 framework achieved unprecedented perfect reliability in real-world robotic manipulation, completing every single one of its 900 test episodes successfully, including 250 consecutive trials on a single task. Second, researchers demonstrated fully autonomous aerial construction using coordinated unmanned aerial vehicles working together to perform complex construction tasks. Third, space robotics achieved comprehensive mathematical frameworks for spacecraft-manipulator systems. Fourth, the RoboGhost framework enables retargeting-free humanoid control through direct language-to-action mapping. Finally, the integration of tactile sensing with visual perception represents a significant step toward more human-like manipulation capabilities. Among these 17 papers, one stands out as particularly transformative: RoboGhost, developed by Zhe Li and colleagues. This work tackles one of humanoid robotics' most challenging problems, creating a direct pathway from natural language commands to robot locomotion. Traditional approaches involve a complex, fragile pipeline where systems must decode human motion from language, retarget that motion to fit robot morphology, then track it with physics-based controllers. RoboGhost revolutionizes this by eliminating intermediate stages entirely, using a hybrid causal transformer diffusion motion generator that ensures long-horizon consistency while maintaining stability and diversity in generated motions. The technical innovation lies in RoboGhost's retargeting-free framework that bypasses explicit motion decoding and retargeting steps entirely. The system uses a diffusion-based policy that can denoise executable actions directly from noise while preserving semantic intent. This requires careful design of the latent space to capture both semantic information from language and kinematic constraints from robot morphology, essentially creating a shared understanding between human language and robot capabilities. The experimental validation demonstrates substantial improvements, significantly decreased deployment latency compared to traditional multi-stage approaches, markedly improved success rates, and new levels of tracking precision accuracy. What makes RoboGhost particularly compelling is its human-centered design philosophy. The researchers were motivated by observing how naturally humans communicate movement intentions through language, gestures, and even music. They recognized that forcing robots through artificial intermediate representations was fundamentally limiting their ability to understand and respond to human communication. The multimodal extensions hint at robots that could respond to gestural commands, musical cues, or environmental sounds, creating more natural and intuitive human-robot interactions. Imagine a construction robot responding to hand signals when verbal communication is impossible, or a household robot understanding emotional context through tone of voice. Looking toward the future, these research advances suggest we're entering a new era of robotics, one where machines don't just follow programmed instructions, but genuinely understand and adapt to human needs and environments. Think of it as the difference between a player piano that mechanically reproduces music and a jazz musician who understands emotional context and can improvise accordingly. The convergence of perfect reliability, natural language understanding, sophisticated manipulation skills, and multi-robot coordination points toward robotic systems that could genuinely transform society. We're moving toward robots that work as partners rather than tools, adapting to our preferences, learning from our feedback, and handling the complexity and unpredictability of real-world tasks. Today's exploration of 17 cutting-edge robotics papers reveals a field in rapid transformation, where boundaries between human and artificial intelligence are becoming increasingly blurred. We've witnessed robots achieving perfect reliability in complex tasks, understanding natural language commands with unprecedented fluency, and developing tactile sensitivity that enables delicate manipulation. These fundamental breakthroughs could reshape how we live, work, and explore our universe. The convergence creates a foundation for robotic systems that are truly intelligent, adaptable, and capable of working alongside humans as partners, rather than mere tools. This content was synthesized using Claude Sonnet 4 model for analysis and script generation, with TTS synthesis powered by Deepgram technology, and image generation through OpenAI tools. Human expert review and validation ensured accuracy and clarity throughout the production process. While every effort has been made to accurately represent the research findings, some oversights may exist. We encourage listeners to consult the original papers on the archive preprint server for complete technical details and to verify specific claims through primary sources. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Subscribe for the latest AI breakthrough coverage, daily insights from top research papers, and expert analysis of emerging technologies. Join our community of AI enthusiasts and never miss the next revolutionary discovery. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses archive.org content under its API terms of use. Frontiers is not affiliated with or endorsed by archive.org.